And welcome back. As we continue our cosmic journey, we're going to go ahead and start looking at things a little closer to home by first visiting the first planet from the Sun, which is Mercury. So let's start first off by talking about Mercury's orbit. Now, Mercury, as I mentioned, is the closest planet to the Sun. It's the nearest, and therefore it has the shortest period of revolution around our Sun, which is about 88 days, and it also has the average orbital speed of 48 kilometers per second. So it's pretty fast because, again, it's the closest planet to the Sun. Now, because Mercury is so close to our star, it can be very difficult to kind of pick it out in the night sky because, again, it's very close. And as you might expect, because of that close proximity, it's best to see Mercury when its eccentric orbit takes as far away from the Sun as possible because it's going to lie so close to that ecliptic, which of course is the path of the Sun, that it's going to be very hard for us to actually make that out. Now, the semi-major axis of Mercury's orbit, which is again the planet's average distance from the Sun, is about 58 million kilometers or 0.39 astronomical units. However, because its orbit has a very high eccentricity of 0.26, Mercury's actual distance from the Sun can vary anywhere from 46 million kilometers to 70 million kilometers. And that's a wide variance. Compare that to other planets such as Earth, Venus, Mars, even some of the gas giants. And you'll see that that eccentricity value is not as large as it is with Mercury. Now, what about the composition of this planet? And this is, of course, something that we might be able to deduce from our previous conversations. But if we start looking at Mercury, its mass is about 1/18th that of Earth, which makes it the smallest terrestrial planet. Mercury is, of course, the smallest planet that is in our solar system, except for the dwarf planets, and it has a diameter of 4,870 kilometers, which is less than half the diameter of Earth. Now, Mercury's density is also 5.4 grams per centimeter cubed, which is much greater than the density of the Moon. So that's an interesting thing for us to look at and say, hey, the composition of these two objects, it differs substantially, even though both of them are, on the surface, they might look like they're very similar. The Moon is, roughly a similar size, and it has very cratered surface like Mercury. But when we start looking at things like the density, we can see that it's not the same. Now, Mercury's composition is one of the most interesting things about it and kind of makes it unique among the planets. Mercury's very high density tells us that it has to be composed largely of heavier materials, such as metals. So, we already said it has high density, so let's look at the structure of Mercury and examine why this composition might be something worth studying. Well, models for Mercury's interior suggest that it has a metallic iron-nickel core amounting to 60% of the total mass, with the rest of the planet being made primarily of silicates. So, again, 60% of that is dedicated to the core. Now, the core has a diameter of 3,500 kilometers and extends out to within 700 kilometers of the surface. And so a good way to think about Mercury, it's really just a metal ball that we can say is about the size of the Moon, that's surrounded by a rocky crust that's 700 kilometers thick. Now, unlike the Moon, Mercury actually does have a weak magnetic field. Remember, the Moon doesn't have any kind of atmosphere or anything like that. But with Mercury, this very thin, non-existent atmosphere does kind of exist because, again, we have this magnetic core that we can kind of rely on. And the existence of this magnetic field that exhibits around Mercury is consistent with the presence of us knowing that there has to be a large metal core inside and suggesting that at least part of that core has to be liquid in order to generate the field. It's not solidified, it has a liquid piece to it, and remember that liquid shifts around, that's what actually allows that magnetic field to kind of spin and generate. Now, Mercury does have kind of a strange rotation to it. Visual studies of Mercury's indistinct surface markings were once thought to indicate that the planet kept one face to the Sun, much as the Moon does to Earth. In Earth, it's tidally locked. Now, for many years, it was widely believed that Mercury's rotation period was equal to its revolution period of 88 days, making one side perpetually hot while the other side was always cold. However, radar observations of Mercury in the mid-1960s showed that Mercury does not keep one side fixed toward the Sun. If a planet is turning, one side seems to be approaching Earth, while the other is moving away from it. And so the Doppler radar can actually be used then to measure rotation. When a radar beam is reflected from a rotating planet, the motion of one side of the planet's disk toward us and the other side away from us actually causes a Doppler shift in the reflected signal. Now, this effect can cause both a red shift and a blue shift when the spread of frequencies that are within the radio beam. The resulting Doppler shift spreads or broadens the precise transmitted radar wave frequency into a range of frequencies in the reflected signal. Now, the actual degree of broadening actually will provide us a very exact measurement of the rotation rate of the planet. And this is what we have to use with Mercury because, again, we have to look at that and grab whatever measurements we need. And we look at the diagram here. In this picture, we can transmit a signal to a target planet. So, for example, in this case, Mercury. This is our transmitted signal. If it would return with no rotation, you can see that it is pretty much exactly the same as the original signal that we send out. However, if it returns with a slower rotation, you can see how the Doppler effect has changed how we would perceive the frequency that we sent. And if it is a faster rotation, again, you can see how this is now widening even further. And that can, of course, give you some good visual information about what this planet is actually doing. So let's talk about rotation and proximity and how they relate back to Mercury. Now, Mercury's period of rotation is 59 days, which is just 2/3 of the planet's period of revolution. So astronomers actually have found a situation where the spin and the orbit of a planet are in a 2:3 ratio can actually be pretty stable. Mercury, being so close to the sun, is very hot on its daylight side, but because it has no appreciable atmosphere, which means, if there is one, it kind of evaporates away. Mercury does have very thin atmosphere, but it's so thin that it a lot of times is washed away in the solar wind. So what happens is it gets surprisingly cold during the long nights. Now, the temperature on the surface climbs up to 700 Kelvin or 430 degrees Celsius at noontime. And after sunset, the temperature drops, reaching just 100 Kelvin or negative 107 degrees Celsius just before dawn. Now, the range of temperature on Mercury is therefore about 600 Kelvin or 600 degrees Celsius, which is a greater difference than we have recorded on any other planet. Again, because this all has to do with Mercury's proximity to the sun. So if we were on the surface of Mercury, you might notice that it strongly resembles the moon in appearance. I already mentioned that it has a very cratered look. It's covered with thousands of craters in larger basins up to 1,300 kilometers in diameter. Now, some of the brighter craters that we can observe on Mercury are rayed, and many even have central peaks. There are also scarps or cliffs more than a kilometer high and hundreds of kilometers long, as well as ridges and plains that we can observe on Mercury's surface. Now, one of the most important discoveries was the verification of water ice, first detected by radar in craters near the poles, similar to the situation that we have observed on our own moon, and the unexpected discovery of organic or carbon-rich compounds that are mixed in with this water ice. So, that begs some questions as to the geologic history of Mercury. The first thing that we are able to notice is that, there's no evidence of plate tectonics on Mercury. However, the planet's distinctive long scarps can sometimes be seen cutting across craters, meaning the scarps must have formed after these craters were done. Such as you can see here in this image here, you can see we have an impact crater, but then we have the scarp that comes across the surface, and you notice it goes through this crater here, which means the scarp came afterwards. These long curved cliffs appear to have their origin in the slight compression of Mercury's crust. At some point in its history, the planet shrank, wrinkling the crust, and did so after most of the craters in its surface had already formed. Now, this shrinkage must have taken place during the last 4 billion years, and not necessarily during the solar system's early period of heavy bombardment. So that gives us wondering about, how did Mercury actually come about? What was its origin? Well, the problem with understanding how Mercury formed is the reverse problem that we have posed by understanding the composition of the moon. We've seen that, unlike the moon, Mercury is composed mostly of metal. However, astronomers think that Mercury should have formed with roughly the same ratio of metal to silicate as what's found on Earth or Venus, because again, it's a part of the same celestial band. So the question begs, how did Mercury lose so much of its rocky material? Well, the most probable explanation that we have for Mercury's silicate loss might be similar to the explanation that we have for the moon's own lack of a metal core. Mercury is likely to have experienced several giant impacts very early on in its youth, and one or more of these may have actually torn away a fraction of its mantle and crust, leaving just a body that's dominated by its iron core. And a recent alternative explanation suggests that very early on, even the heat from the young sun evaporated much of the lighter, more volatile silicates in the material that formed Mercury, leaving the planet with a majority of metals.